So after we have imputed all the missing values and have cleaned up our data set, we can do a basic characterization. So for example, we check in a histogram, what do the overall data look like? So we see a distribution like this, where we have a nice skew towards the essential genes, but most of the genes hover around 0 and are non-essential. But there's this nice tail here, which is the essential genes here. Then we can look at ATR. And for example, here are two different plotting functions. I use again this subplot method to plot two columns of data in one row. And in the first column, I show a histogram where you show the median and the mean value of the ATR. And you see there's a few outliers here. And it's a very essential gene with a mean of minus 1.5 gene dependency score. And we can also look at the box plots to look at the distribution in breast and in myeloid cancer, for example. So things like that. But now, as we're done, let's talk a little bit about the next step, which is now the real correlation analysis workflow. So for this, what we have to do is we first have to get the data for just the ATR. So if we do filter GeneDF with ATR, we just get a single column of data, a single list of gene dependency scores that are the gene dependency score for ATR. And then we exclude ATR and get the rest of all the gene columns. So this is here just getting just the numeric columns. We don't want to deal with the metadata. And we just use the drop method to get rid of ATR. And that gives us all the genes except for ATR. We don't want to correlate ATR with ATR. That would just give us a straight line, basically. And then now this is the core function that you need to understand. This is the actual calculating the gene correlation function, where we have, so what we're doing, we're collecting data. We're collecting two different data sets, and I'll explain you what that means in the next slide. So we collect data that tell us how linear are the correlations. And there's two methods, the Pearson method and the Spearman methods. So we will, in these lists, we will start catching these Pearson correlation coefficients and Spearman correlation coefficients. And then we're also analyzing the p-values, so the statistical relevance of these correlations. And so there's a for lists that we are starting off as empty. And then we are doing a for loop across the gene names. So we say in other genes DF that we've defined here, we've excluded the ATR from the numeric columns. So this will be the list of all the gene names in the data set. So we can cycle through this list. So we say for gene in all these gene names. We first get the actual data for each individual gene per cycle, per iteration. So here, this will give us, again, one single row of data, or one single column of data rather, for the particular gene that we're at in the iteration cycle. And then we can compare our ATR values that we've collected before with the gene values other, which is just a single gene value which will change in each iteration. And that will, and we're using these Pearson R functions from scipy, and I'll explain you that in a minute as well. That will collect this the coefficient and the p-value, and also the same for Spearman coefficient and p-value. And then we can append this data into these four different lists. So we're collecting the data, append them, and the for loop will be, so in each iteration, each of these lists will grow by one. And in the end, we can collect all of this back into a new data frame. So we haven't done it before, but this is a very simple method of building a new data frame. We build first the dictionary, where we have our column names, which is gene, and then we put in the list. So genes is the gene names, Pearson R is the Pearson R coefficient, Pearson P is the p-values, and so on. And this dictionary can then just be added as a parameter for the PD data frame method, which will build the results DF. And then in the end, the function returns the data frame. This was quite a lot to go through. But I've actually this building, cycling through data frames and building new data frames is a pretty common pattern. So I generated a practice notebook for this coding pattern as well. So go through that. We'll start very simple and then end up so that you understand. And this is something that is quite a kind of common pattern in working with pandas. So it's good that you understand that. In the end, we get a new data frame where we have a column with all the gene names, and then a column with the Pearson correlation coefficient and the Pearson p-values and the Spearman values. So quickly, what actually are these values? What is Pearson and Spearman? So these are mathematical expressions that give you an idea how linear the relationship is between two data sets. And the formula for Pearson correlation is here. You don't really need to understand the maths behind it. What you need to understand is that it's a number between 1 and -1. If it's 0, there's no correlation whatsoever. If it's 1, it's a perfect positive correlation, so a line that is going up. And if it's -1, it's a perfect negative correlation and a line that's going down. And we can also calculate the statistical significance of this using, and that will be done in a p-value. That's the beauty of coding, is you can use these quite powerful functions without really having to chunk through the data and understanding exactly the maths of it. But if you really want to use this a lot, it's worth going into detail and really finding out how exactly it works. But you can get productive very quickly just using the packages, the statistical packages that are available. As long as you know what these values mean, they will give you can do quite powerful work with this. We also have a second way of doing it, which is Spearman correlation, which is similar, but it's more robust to outliers. So Pearson will give you very quickly some pretty significant values if there's outliers that skew the data, and Spearman is a bit more robust to that. But what we are doing is we're calculating both, and if the genes that we find are giving you significant values in both, this just increases confidence. And here I need to say it's very rare that you get a correlation like this, which is completely perfect. Usually you're in quite noisy territory, and then it becomes quite dangerous. So we will talk about false positives in the next lecture anyway, but correlation doesn't necessarily mean a causal effect as well. So there can be by chance correlations. If it's completely correlated, you can be pretty sure that there is a causal connection, that these two genes will have something to do with each other. But mostly our Pearson values will be between 0.5 and 0.2. So there it becomes quite, you have to do additional analysis to gain confidence that the correlations that you're looking at are actually meaningful at all. Great. So how do we calculate the Pearson, the Spearman? Where do these functions come from? That's the last thing I'm going to do in this session here. So we can use I'm introducing a new package here, scipy. And this is a collection of function and methods for scientific computing. There's quite a lot of powerful tools in there, especially for linear algebra, for integration, interpolation, for signal processing. Mostly in biology, we will focus around the stats package, which gives us, and we'll have a few more stats functions later on, which we are using here, which gives us function to do statistical analysis, like t-tests, for example. But in our case, the Pearson and the Spearman are. And the Pearson R we import from scipy.stats. We import the Pearson R, and then these functions return the correlation coefficient and the p-value, and we just have to supply two lists of genes. So gene 1 on the x-axis, gene 2 on the y-axis, and then it gives us so if this value is 1 and the p-value is very, very small, we know this is a highly linear correlation. And same with the Spearman R. So that's the gist of it.